The idea behind this topic is we have already discussed the gas laws and led us to talking about the ideal gas law. But what if I don't have ideal conditions, or if I have one or more variable that I can solve, that I can use, solve for solving a problem? And in this case, I'm going to use or show you how to use the general gas law. And we will continue by talking about the application of the ideal gas law, which is determining the density and molar masses of unknown gases. Now, this is just a refresher over the three laws that we've determined or learned about so far. So the first one is Boyle's law. According to Boyle's law, that at constant number of moles and temperature, pressure is inversely proportional to volume. And we can use this relationship to either find a pressure, missing pressure or a volume. And one here, we said it's initial and then final. Charles' law indicates that at constant pressure and temperature, volume is directly proportional to temperature. All right, and we used this setup to determine either a missing volume or temperature. And finally, Avogadro's law at constant pressure and sorry, I said in Boyle's law, on Charles' law, at constant pressure and temperature, it's constant pressure and number of moles. My apologies. And then, according to Avogadro's law, at constant pressure and temperature, the volume is directly proportional to the number of moles. Now, in ideal situations, we can rearrange the ideal gas law, which is PV equals to nRT, and say that PV over nRT equals 1, and 1 here indicates the ideality. But what if we don't have ideal conditions, or two or more quantities are available? Therefore, all these laws can be combined together to give me this setup, which is called the general or combined gas law. And this applies if one or more gas properties are held constant, okay? So for example, if N, or number of moles, are held constant, I will have the setup because simply the number of moles is going to be the same. Now let's see how we can apply the combined gas laws to problems. So say we have two containers of gas at the same pressure and temperature. So same pressure, same temperature. So let's write here a note, constant pressure and temperature. So what does that mean? If I write my combined gas law right here, that means that the pressure and temperature will go, and therefore I'm working with the volume and moles. Okay, so in this case, really, it's Avogadro's law. I'm kind of working with Avogadro's law. So in this, let's read the rest of the problem. One container has 1.38 moles of fluorine gas, and twice the volume of the container has the carbon dioxide gas. What mass of carbon dioxide is in the other container? So in this case, I can say that if volume, the initial volume, equals to twice of the final, therefore I can say that 2VF over 1.368 moles equals to VF over N final. Therefore, N final equals to 0.6840 moles of CO2. And And in this case, I can say that if I find the number of moles, it asks what mass, so I'll use the molar mass, which will give me here 30.10 grams of carbon dioxide. Now let's track our sig figs. We only have this one number, so it's going to be 4 sig figs. Now, let's look at quite a different example. And for this example right here, we have a sample of carbon dioxide with a volume of 1.56 liters, pressure of 7.6 times 10 to the third, and 25 degrees Celsius. And asks here, what is the new volume if the pressure and temperature is increased to 2.75 and 65 degrees Celsius. So we're working with a initial pressure, initial volume, and initial temperature, according to the combined gas law. I'm going to assume that the number of moles are going to remain of the gas are going to remain constant. So in this case, I can say that P final over TF. Now, let's look at the pressure, which is 7.6 times 10 to the third pascals. Now, I need to switch it to be the same as the other pressure. It doesn't matter which one I switch to. I'm just going to switch to atmospheres because this makes more sense as a conversion. Okay, and then times the volume, which is 1.56 liters, divided by the initial temperature, which is 25 plus 273.15, and will be equal to the final pressure, which is 2.75, times the volume, which I want to find, divided by 65 plus 273.15. Now let's look at the sig figs. We have here 2 sig figs, 3 sig figs. Right here, this is infinite. This operation gives me here 298.15, and is going to be a whole number because my temperature has no decimal places. So as here, 338.15, 3 sig figs and 3 sig figs. Therefore, my final volume will end up with 2 sig figs and becomes 2.04825734923 liters, and is going to be here 0.048 liters. Now, another thing we want to know about, or you want to know about, is the standard temperature pressure, or STP. And STP are very specific conditions, meaning that for at STP, or specific temperature pressure conditions, are 0 degrees Celsius or 273.15 Kelvin, and the pressure must be 1 atmosphere. Now, the standard temperature pressure condition gives rise to something called the standard molar volume. At the standard molar volume and under standard temperature pressure condition, 1 mole of ideal gas occupies exactly 22.4 liters. And this comes from the ideal gas. PV equals to nRT. So I can say that 1 atmosphere times volume equals to 1 mole times 0.08206 liter atmosphere mole K times 273.15. Therefore, volume here can be 22.414689 liters. Okay? Or I can say that if 1 atmosphere times 22.4 liters equals to N times 0.08206 times 273.15, therefore N equals to 1 mole. So this right here is a valid relationship. And we can use these conversions only when it's mentioned in the question that I have standard temperature and pressure conditions. Now let's look at an example. The examples, I don't think they're too bad or too hard, but we can work on a problem to see how it goes. Now, if I have here hydrogen and nitrogen gas react to form ammonia, that means I have to write an equation. So I can say that hydrogen and nitrogen react to form ammonia. Okay, let's balance the equation. And it wants you to find if how much grams of ammonia are formed if 0.467 liters sample of hydrogen reacts with this excess nitrogen at, and see it mentions here, at standard temperature pressure conditions. So it's basically a mole-to-mole conversion using the mole-to-mole ratio in the equation, but we will use the standard temperature pressure conversion to convert from the liters of hydrogen to moles of hydrogen, and then to moles of ammonia, and then to mass of ammonia. So let me show you. So we can say that 0.467 liters of hydrogen, and here 1 mole over 22.4 liters times 2. So for every 3 moles of hydrogen, I have 2 moles of ammonia reacting. And finally, it wants the grams of ammonia, so I'm going to use the molar mass of ammonia to convert to the mass of ammonia. Now let's look at the sig figs. 3 sig figs, 3 sig figs, and then 4 sig figs. So the answer here should be 3 sig figs, 0.236835714 grams ammonia, and it's going to be rounded to 2.237 grams of ammonia. It's really simple. The only thing is, do not use this conversion right here if it's not STP. It must mention in the question that it's STP. Now, another thing is we want to talk about is the application of the ideal gas law and how we can actually rearrange this equation with a slight, or not rearrange it, do a slight modification to it so we can determine the density of a gas. And usually it's going to be in grams per liter, or we can convert it to grams per milliliters, and the molar mass of unknown gas. So we can say that if we look at these equations right here, we can say that the number of moles of a gas equal to the mass divided by the molar mass, okay, in grams per mole, and which equals to, and N also happen to equal to PV over RT from the ideal gas law. And if I rearrange it, I get that mass times RT divided by PV. And note right here that if I just isolate this fraction right here, this right here is density. So I can use this also to determine the density of an unknown gas by rearranging the equation. And now let's look at 2 examples. So the first example right here is that air has an average molar mass of 29.0 grams per mole. What is the density of the air at 0.99 atm? So in this case, it wants here to determine the density of the air. So in this case, I can say that molar mass equals to density times RT over P. And the molar mass is given to me. And if I'm going to rearrange the equation, therefore, density equals to molar mass. This is molar mass times pressure over RT, which right here is 29.0 grams per mole, times the pressure, which is 0.99 atm, divided by R, which is 0.0206 liter atmosphere over mole K, and times the temperature 30.0 plus 273.15. And let's look at the sig figs. 3 sig figs, 2 sig figs, 3. And right here, I'm going to end up with 4 sig figs because it has 1 decimal place. Therefore, the lowest sig figs is going to be 2 sig figs. And I get right here that 1.1541077 grams per liter. And if I round it to 2 sig figs, it becomes 1.2 grams per liter. Now let's look at another example. What it wants you to determine the molar mass of the gas. So again, same idea. We can say that molar mass, because it asks here in the question molar mass. So you have here a 0.1418 gram sample that has a volume of 150 milliliters at 66.3 degrees Celsius and 99.0 kilopascals. What is the molar mass? So molar mass equals to mass, which is in grams, times RT over PV. Again, very simple, plug and chug, and times temperature 66.3 plus 273.15. Again, this is in liter atmosphere mole K. Everything has to match, divided by, I'm going to convert this right here to atmosphere to match the units for the gas constant times volume, which is in milliliters, but I'm going to convert it in liters again because of the units. And let's track my sig figs. 3 sig figs, 4. I'm going to end up here with 4 sig figs because of the decimal place. And 3 sig figs, 3 sig figs, then my answer should be 3 sig figs. And from this operation, I get 1.103.62563.024 grams per mole. And if I'm rounding just to 3 sig figs, this is going to round up to 104 grams per mole.